Hello.
Hi, Syed. How are you doing?
I'm doing fine. How are you?
Not too bad. Okay, let's let everyone through.
Okay.
Oh yeah, I keep forgetting to. I'll just disable the waiting room.
Okay.
Let's since we have some time before we start, let's do a round of questions. So if anyone has any questions, go ahead. Let me post. Let me put the link to the YouTube just in case. Um,
So Isaac has a question.
okay, just 1 second. I'm just about ready here. Okay, Isaac, go ahead.
Yeah, actually, it's quite simple. Just do we have a quiz today?
Why, you want to go back to sleep?
No, just like asking.
Not today.
Thanks.
You're welcome. Anyone have any other questions?
Hi, sir.
Hi. Who am I
When
talking
could we
to?
have a when could we have assignment A?
It should be either today or tomorrow,
Okay.
and that's
Thank
not
you.
going to be due until the week after reading week.
Okay.
I'm just going to look at the chat here. So someone says going to get some sleep next week. Plenty of sleep. That's a good idea. Very good idea to get some sleep. I recommend that you get not only getting sleep, but also since the well, I'm not sure how many of you are in Toronto, but if you're in the north like we are here in Toronto, you're not going to get enough light. You're not going to get enough sunlight. So this is a problem for everyone, everyone here. And so a lot of people, what we do is we have special blue lights or special high spectrum, full spectrum lighting that you look at for a certain amount of time per day. And this prevents you from falling into this SAD, seasonal affective disorder. A lot of the faculty use it all the time in the winter. A lot of my students use it. So I highly recommend it. You're not going to get enough sunlight. Have you ever used that, Syed, by any chance?
I personally have not. but it does sound like a good idea because I'm in a
Yeah.
basement with no windows.
Yeah, it's a very good idea. Everyone should consider it. If you're not getting enough light, then you should consider it. I have a light that I can wear as like glasses so that I can walk around and have the light therapy. And it really does work. Yes, absolutely. The other thing that you should be doing is getting exercise. So you should sleep, get exercise, and get enough light. That's what your therapy regimen should be for the reading week. Because if you're not exercising, you know, you're going to fall into a slump. That's for sure. Any questions, math questions? Let me just share my screen. Okay, so just top 3 recommendations. What was it? SAD lamp. And what was the third one? Sleep. Got it? I'm giving this for free, all this advice. Free. Normally you'd have to pay quite a lot of money for this kind of thing.
I mean, we're paying tuition.
Yeah, but you're not paying tuition for this kind of advice. This is bonus. Okay. All right. So we've done a lot of construction. So we're at a kind of midpoint now in the class. We've talked about vector spaces over fields, over different fields. We've talked about the notion of dimension. So we've talked about fields. Well, we've done a lot on sets and maps. We've talked about algebraic structures. Groups, fields, etc. We've discussed vector spaces over a field. And within vector spaces, we've been focusing on a few different things. There's the notion of linear dependence or independence, the notion of dimension, other things like subspaces and operations on them. We've talked about so this is linear independence and span, dimension, subspaces. We've also talked about the Gaussian elimination. Algorithm. Okay, and and maybe something that is kind of so important that maybe it deserves its own heading, which is linear maps between vector spaces V and W. And this is some, linear maps have a null space and a range. We have a notion of isomorphism, invertible maps. Finding inverses, finding the inverse. Oh, well, okay, maybe I'll put this first. Then very important matrices, matrix representations of linear maps, finding inverses by bookkeeping, elementary row operations, and solving linear homogeneous or inhomogeneous systems. So we've done all of this. And I should say, let me just put in here, not only did we talk about matrices, but the dependence of the matrix on the choice of basis. So change of basis was also covered. So this is the idea that whenever you have a linear map, you choose a basis for the domain, you choose a basis for the codomain, and that expresses your linear map as a matrix. And if you change the two bases, the one on the domain and the one on the codomain, this basically multiplies your matrix on the left and on the right by change of basis matrices, right? Which look like this was something like this, that if we took our linear map and we expressed it in terms of, let's say, beta and gamma bases, right? But if someone provided a new basis beta prime for the domain and a new basis gamma prime for the codomain, then in order to find the matrix of the in the new bases, we would need to figure out two matrices, one on the left, which is the change of basis going from gamma to gamma prime, and one on the right, which is the change of basis from beta prime to beta. And when we multiply these together, we get the matrix of our linear map in the beta prime gamma prime basis. So this was a kind of important set of ideas, which is the way that these things change when we change the basis. So that, I think, is pretty much all the stuff that we've covered so far. Any questions or comments about this?
So there seems to be a request in the chat if we can make the background a bit darker to improve the contrast.
The background, like the gray background of the page, you mean?
It seems like that's what they're requesting, yeah.
No, I don't think so. Maybe maybe this will be better. I can't change the background color of the page, apparently. Yeah, because they have a dark and a, let's see, where is it? Paper color. Oh, dark. Yeah, there is no, for some reason, no selection there. Okay, so the next part of the class is going to focus on linear maps from a vector space to itself. Okay, so this seems like a small modification, but it actually turns out to be a much bigger modification than it looks like. So, so we would like to classify, understand linear maps from a vector space to itself. So you have to understand that there's a big difference between mapping from a set to itself, or between that and mapping from a set to another set. The reason is that we have such things as fixed points. In the case of sets, we saw that there's such a thing as a fixed point. There's such a thing as a permutation where we have cycles of points that are cycled around by the map from the set to itself. These ideas of fixed points and cycles and such things, they don't exist for maps between two different sets. Between two different sets, all you can say is, where does each point get sent? It doesn't make sense to ask, what are the points that are sent to themselves? Okay, so in that sense, the theory of maps, self-maps, is more complicated and interesting than the theory of maps from one place to another. Okay, and this is where we are going to get ideas like fixed points, fixed vectors. No, it's not called fixed vectors, but it's called eigenvectors, eigenvectors, or eigenvalues. And generalized eigenspaces. And so there's this entire theory of eigenspaces, which is really fundamental for this. And so we're going to go through all that after the reading week. And and the classification of these, there's different classifications, but the most famous one, and the one that we're going to try to get to, is called the Jordan canonical form. Oh, and I forgot to mention that we will have we will also have a discussion of determinants, so that will come up as well. So that's one topic, and then there's a topic on determinants, and that will basically complete the material that we want to cover. So today I just want to go through something really important, which fits into the first part of the class, and which you saw a little bit of in the assignment. Oh, I should have also mentioned up here that we did something really important, which was we talked about quotient spaces. This was in the assignment as well, V mod U. Okay, so today what I want to talk about is duality. Okay, so I'll start right away with the definition. So let V be a vector space over the field F. Okay, the dual vector space V dual is by definition the linear maps from V to the field. Maybe okay. So in other words, these are linear functions. The space of linear functions, or sometimes called functionals, and sometimes called forms, linear forms. It's an old idea, so it has a lot of different weird names, but it's just a dual space. We already saw that linear maps between vector spaces themselves form a vector space. So it's no surprise that V dual is a vector space, right? So if alpha 1, alpha 2 are in V dual, then, you know, just as before, as for any LVW, these form V star is a vector space where if I take lambda, apply it to alpha 1 and add alpha 2, this is supposed to be another linear function which takes a vector to alpha 1 of the vector that alpha 1 evaluates on V, because alpha 1 is a linear function on the vector space V. So if I take a vector in V, I can evaluate alpha 1 on V and I'll get an element of the field. Then I can multiply by lambda and I can add this to the value of alpha 2 on V. And this is the sum in the field. And this is the multiplication in the field. Okay. But this is the sum in V dual. And this is the scalar multiplication in V dual. Okay, this is just a remark. It's not part of the definition. The definition should be clear by itself. I just wanted to spell it out just in case there's any confusion. Okay, now, okay, so let's say, let me just do a proposition right off the bat. So suppose that V is finite dimensional. Okay, then the dimension of the dual space is equal to the dimension of V. Okay, so how are we going to prove this? The way we'll prove it is going to be useful for thinking about the dual space in general. So we're going to prove it by exhibiting a basis for the dual space and then seeing the length of the basis. So the strategy is that we will construct a basis for V dual. Okay, and the way that we're going to do it is by choosing first a basis for V. So let's say that beta is a basis for V. Okay, so now think about it like this. So we're trying to understand the dual space. We're trying to understand the linear functions on V. Now these linear functions, any one of these linear functions, right? If I have, let's say if if alpha is a linear function, so if we have a linear function, then, and if we want to understand how this linear function evaluates on a general vector, okay, then what you can do is you can expand the vector in terms of the basis. Let me just write it as AIEI. So I've expanded my vector in terms of the basis, and then alpha v will be equal to this, alpha of a combination, a linear combination of basis vectors. And because of linearity, this can be expressed as a sum of AI alpha vi. So you see that that if we know the value of alpha on the EI, okay, we can determine the value on V. I'm not saying anything particularly deep here. It's a linear function. So if you know it on a basis of V, you're going to know it on any vector in V. Okay, so so if you think about it, that means that any linear map, any alpha, is going to be determined by its values on the EIs. So it's going to be determined by n values. That's how much freedom there is in the determination of alpha. There's n degrees of freedom. There's n numbers in the field. What is alpha's value on E1? What is alpha's value on E2? And all the way up to its value on En. If you know all those values, those are going to be n numbers in the field, and that will tell you basically what alpha is. Okay, so that means that you can tell right away that the dimensionality, the dimension of the dual space is exactly n, because each dual vector is determined by n values. N, it's an ordered tuple of n numbers in the field. Okay, so I just wanted to make that as a kind of as a remark. In other words, just to summarize, alpha is determined by n numbers in F, alpha E1, alpha En. So we should expect, so I'm just giving the kind of heuristic explanation for what is going on, why the dual space should have the same dimension as the dimension of V. Okay, but I still wanted a basis. So I want, among all possible linear functions, I want to select some basic ones which will form a basis. So I want some elementary ones out of which every other linear function can be built. So in other words, what would be the simplest possibility of a linear map evaluating on the basis? The simplest possibility would be to have a linear map that evaluates on E1 to give the number 1 and evaluates on the rest to give 0. So this is like an indicator function which evaluates to 1 on the first basis element and 0 on the others. So we're going to try to build a basis as follows. Okay, and I'll call them the first one I'll call E1 dual. So E1 dual is going to be defined as follows. So E1 will be sent to 1. E2 will be sent to 0. and the rest of these will be sent to 0. And now that I've determined its values on a basis for V, then you can figure out what its value is on any vector at all. Okay, and E2 star, what will it do? Well, it will do the same thing. E1 will be sent to 0, E2 will be sent to 1, and E3 will be sent to 0, and the rest will be sent to 0. Okay, and so on. Okay, EJ star evaluated on EI is equal to 1 in the case that I equals J, and is 0 else. Okay, so now I have E1 star all the way up to En star, and the claim is that this list of linear functions forms a basis for V star. So okay, let's prove that it spans. Okay, so I need to show that anything in the dual space. Sometimes the elements of the dual space, by the way, they're called covectors. Vectors in V star are sometimes called, linear functions, functionals, linear forms, or covectors. Okay, so I want to show that these n covectors span the dual space. So if so let alpha be any element of the dual space, and define these numerical quantities AI to be the value of alpha on the EI. Okay, so I want to know which dual element I have in my hands, alpha. So in order to figure out what it is, I need to evaluate it on the basis. I get these n numbers, and then I can reconstruct it. I can say, well, okay, if I need to build this alpha out of the basis, of the supposed basis, I need to make sure that, if I use E1 dual, I'm going to, have a coefficient in front of E1 dual, a coefficient in front of E2 dual, and so on. I need to show that there are coefficients which make this this inequality, that alpha is in the span of the EI dual. So the question is, well, okay, what will happen when I apply alpha to EI, or to E1, let's say? When I apply alpha to E1, all of this will vanish. And the only term that will contribute is this one. Okay, so if I apply alpha to E1, I will get whatever this coefficient is. Okay, so if I know what alpha is on E1, in other words, if it's A1, then I can just put it in here, A1, A2, and so on. So then we get this this expression for alpha. Okay, so this shows that I'll call this beta star. Beta star spans V star. Any questions about that part, which shows that these n covectors actually span? Okay, and then if I want to show that they're linearly independent, you can say, oh, suppose that I have bi ei star from 1 to n. Suppose that this is equal to 0. Suppose I have a linear combination of the dual vectors, which is equal to 0. This implies that, well, okay, so we want to show that the BIs are 0 for all I. Okay, that would show that the EI star are linearly independent. How do I show that each of the BIs is equal to 0? Well, this is a covector. It's ready for you. It's ready to gobble up a vector and spit out a number. Okay, so if I feed it one of my basis vectors, but if I take this sum, okay, and I evaluate it on, let's say, EJ, okay, what am I going to get? Well, again, the EI stars are going to send EJ to 0 unless I is equal to J. So the only thing I'm going to get here is BJ. But this thing here, I'm assuming that the total sum is actually 0. Okay, so this is equal to 0. So we get that BJ is equal to 0 for all J. Okay, so we've successfully produced a basis beta star for V star. And so we see that they have the same dimension. Okay, and we can even use this to define an isomorphism from V to V dual. How are we going to do this? Well, V has a basis beta. And that, so by sending, or just by defining T to be such that it takes the basis element EI of V to EI dual, a basis element of V star. If I tell you what this linear map does to a basis, then you can figure out what it does to everything. So it's well defined, and you can see that that it has no kernel. So this has no kernel, no null space, has 0 null space. Therefore, it's injective. But the dimensions are the same. So this tells us that T is invertible. And it's no surprise that it's invertible. The inverse will take EI star to EI. Okay, now here I want to put a little tiny caveat, a little tiny kind of warning, which is that I need to put a subscript on T, and that subscript is beta. Or maybe I should put it, just as a warning. T depends on the choice of beta. We chose a basis for V, and that basis gave us a basis for V star, and it allowed us the possibility of sending EI to EI star. Okay, but this map actually does depend on this choice, and it's not natural. There is no natural isomorphism. So what I mean by that is that there is no way of defining an isomorphism without making a choice. You need to make this arbitrary choice of basis in order to get this map T. Without that, you do not have any map between, you don't have any natural map between V and V star. Okay, so I'm going to continue talking about the dual for the rest of the class today. But so far, what I've explained is that what is the dual, and the fact that the dual has the same dimension as the space itself in the case that it's finite dimensional. And I've explained the relationship between a basis for V and the induced dual basis for V star. Okay, any questions about all that? There's got to be at least one.
Nick, you have a question?
Yes. Just a quick question. How come a zero null space implies that it's injective? I'm sorry, I missed that part.
Okay, so if you have if you have a map from V to W, it's a linear map.
Mm-hmm.
Okay, and if suppose we have x and y in V, such that t sends x. Suppose that x and y are in V are distinct.
Mm-hmm.
Okay, and such that tx is equal to ty. Suppose it fails injectivity.
Okay.
Okay, then we're going to make use of linearity now by taking the right-hand side over to the left-hand side. So this will imply t of x minus t of y is equal to 0. And this, now using linearity of t, this implies that t of x minus y is equal to 0. Okay, so we have now a vector which is in the null space of T. The non-zero element x minus y is in the null space of T. So in other words, the null space of T is not trivial. So you see, like, failure of when we require something to be injective, it means that you cannot have 2 points that are sent to the same point. Okay, so when we talk about injectivity, let's say, of a map from V to W, right, it means that we cannot have the following situation. So we're concerned about the idea that 2 points will both be sent to the same point. So this is not good, right? This fails injectivity.
Yeah. Uh-huh.
But because we're in a linear situation,
Mm-hmm.
right, what that means is that, since this vector and this vector are both sent to the same space, that means that if we take the difference between the vectors, okay, that is a vector like this, and it will be sent to 0. So if you have 2 vectors sent to the same vector, then the difference between those 2 vectors will be sent to 0, and therefore it will be in the null space. So requiring the null space to be 0 prevents this from happening. It prevents the possibility of having 2 points x and y which are sent to the same vector.
Oh, okay. That makes sense. Okay.
Okay, so the existence of a null space, this is the null space.
Yeah.
Okay, and the fact that we have a null space means that if, wherever a vector is sent, if you add something to the null in the null space to that vector, then it will be sent to the same thing. And so killing the null space is the same thing as, preventing the null space from happening is the same thing as preventing, is the same thing as kind of imposing injectivity.
Okay.
It's very similar to the requirement that the range is the whole space. That, of course, is the same as surjective.
Okay, yeah. Yep, thank you.
You're welcome. Okay, any other questions?
Shizuo, you have a question?
Go ahead.
Yes, and my question is, for LVW, linear vector space of map from V to W.
Yeah.
Could we say that the dimensions of this vector space is the product of the dimension of V and the dimension of W?
Yes, that's right. So that's right. So in order to determine a linear map from V to W, you need a certain amount of information, right? You need to know where each basis element of V is sent. But each basis element of V will be sent to a linear combination of basis elements of W, right? And so there will be whatever the dimension of W is, that's how many numbers I will get from each basis element of V. So in the end, you can repeat the argument that I made here, and you can see that every one of the basis elements for V is sent to a linear combination of basis elements of W with a certain number of coefficients. So that means that the total number of coefficients that you need to know is exactly n times m, or the dimension of V times the dimension of W, which is maybe not surprising because we know that these things are represented by matrices in F m times n, or k times n, where n is the dimension of V and k is the dimension of W. And so that means that the total dimension is n times k. That's how many numbers are in a matrix. And that tells you the dimension of the space of linear maps. So this is a special case. The case of the dual space is a special case where the codomain is just one-dimensional. And so you just get the same dimension as V. Yeah, thanks for that question.
Okay, thank you.
Okay, now, okay, so one thing that I want to explain, which is really important, is that we talked about duality, duality of vector spaces. So duality applies not only to vector spaces, so V is sent to V dual, but also to linear maps. Okay, and this is the key idea, which is going to be confusing the first time you see it, but you have to meditate on this. So suppose that A is a linear map from V to W. And let V dual, W dual be the dual spaces. Okay. Now look at what can happen. So I'll draw a diagram. So we have V, we have W, and we have the field, which I'll draw down here. Okay. And the, if alpha, let's say, let me just use the letter F for a dual element in W, a covector in W star. So this F, what does it look like? It's a map from W to the field, a linear map from W to the field. So if we have a map, a covector, a linear function on W, now look what we can do. A is given as a map from V to W, and that's linear. Well, okay, so what does that mean? That means that I could, if I wanted to, I could compose A with F. What will I get if I do that? Well, I will get a linear map from V to F, which means that that will be a covector, a linear map on V, a linear function on V. So this, I'll give it the name A composed F. Okay, so then F, I can compose F with A. And what will I get? This will be in V dual. Okay, very simple, just composition with A. So in other words, given something in the dual space of W, we obtain, through composing with A, through composition with A, we obtain an element of V star. Okay, and so what we're going to give this a name. This is what we call the result of A dual applied to F. So this is by definition of A star. So A star is the transformation which takes F to the composition of A with F. And the cool thing about the dual of A is that it goes in the opposite direction. So A goes from V to W, but A star goes from W star to V star. So let me just draw a picture of that. So we have V, we have W, and we have A. We have W star, we have V star, and A star goes the opposite way. This is a linear map, and this is the dual linear map. Okay. You know, it's like if you think about it, if you know, if V and W are my house and your house, right? And if I go to your house, if I come and invade your privacy, so I'm going to visit you at home, right? So that means that an element of V is going to be sent to an element of W. But our homes are of a different temperature. I like to keep my house really cold. You might like to keep it at room temperature, or maybe even hotter than that. Okay, so if I go to your house, what's going to happen is that whatever your temperature is, whatever your linear function is, the function of temperature, it will then apply to me. It will impose itself on me, and I will then take on the temperature that is at your house. So I'm walking into your house, but my temperature function changes to your temperature value. Okay, so you move an object from V to W, the functions go the other way. So this phenomenon is called contravariance. This is called contravariance. Okay, it's showing you that the way that spaces behave, if you go in a forward direction, you know, in terms of maps of sets, then functions go in the opposite direction. If X goes to Y, functions on Y go to functions on X, not the other way around. That's a very general principle, and it's the basis of what's called algebraic geometry. In algebraic geometry, you always have like maybe a curve inside a space. And then as a result, the functions on the space become functions on the curve. Because the curve is sitting in the space, you can restrict the function to the curve and you get a map the other way. So there's this contravariance is very basic. It occurs in linear algebra, but in all other parts of mathematics. Okay, now, now the last thing is I want to discuss just in the last couple of seconds here, a couple of minutes. So suppose, let's say beta is a basis. Let's say beta is a basis for V, and gamma is a basis for W. Okay, and suppose that this gives beta star EI star for V star, and this gives gamma star, which is Fi star for W star. So the choice of a basis for V and a choice of a basis for W, okay, this allows us to write A in this basis. So let's say that A has basis, has matrix, in beta and gamma. Okay, suppose that this looks like this: A11 up to AK1 up to A1N up to AKN. Okay, so what I want to point out is this following fact, that the fact that I chose beta and gamma means that I can write A as a matrix. Okay, but it also means that I have beta star and gamma star, which are bases for the dual spaces. And therefore I have basis automatically for V star and W star. And that means that I can write A star in a matrix too. Okay, so I can take the dual map and write it now. So what do I need to use? So A star, it doesn't go from V star to W star, it goes the opposite way because of contravariance. And therefore, the domain is W star, and that basis is called gamma star. So it makes sense to write this. Okay, and what will this be? Well, because it's going, if this has dimension n and this has dimension k, this also has dimension k, and this also has dimension n. We proved that just in the last couple pages. So A is a k by n matrix because it's going from an n to a k. But A star is the opposite. It's an n by k matrix because it's going from a k to an n. And what is the n by k matrix? Okay. Well, maybe it shouldn't be too surprising, but it is exactly the same matrix as that of A, but flipped over so that it becomes n by k. Okay. So this is the claim. I'm making a claim here, and what you should do is check this. I could have put it as an assignment question. Okay, so the claim is that the matrix entries of the dual map can be obtained from the matrix entries of the map, the original map. And the way that we obtain it is by taking the matrix and reflecting it about the diagonal. Okay, and this, if we call this matrix M, this is what's called M transpose. So the claim is that the matrix of A dual is the transpose of the matrix of A. Okay, and so the reason that I wanted to tell you all this is so that we have kind of discovered the real meaning of transposing a matrix. You know, when you learn transpose of a matrix, you often just say, well, okay, if I have my matrix, then you just take this diagonal and reflect, right? And you're going to get something that looks like that. Okay. And then you might say, well, why should I reflect it that way? Why shouldn't I reflect it about some other diagonal, or, you know, flip it upside down, or, you know, there's so many things that you could do to a matrix. What's so special about taking a matrix and flipping it around the diagonal? And the answer is this, that the purpose of transposition of the transpose matrix is that it represents the dual map. Okay, I'll leave it there, and we have office hours. So Have a good weekend and have a good reading week. There are no tutorials during reading week. There's no assignment on reading week, but I'll upload in the next day or two the assignment, the next assignment. Okay, yeah. Questions?
Germanjoe, you have a question?
I was just wondering, like, you know how we for past previous time, I don't know exactly which one, but we talked about the particular linear mapping from from the set of n by n matrices to F, the trace. So I was wondering, in for that particular linear map, would that be in the set? Would that be in the dual space of? Okay, wait, sorry. You know what? Actually, let me just think about
Just
this.
continue. Just continue.
Okay.
Finish what you were saying.
Okay. Okay. So, okay. So the way, from what we were discussing today, I guess the trace would be, an element of the dual space of f n by n, right?
That's right.
Okay. And it was I remember we had to prove that the trace was an invariant over bases, right?
What do you mean? Maybe be a bit more precise.
Okay.
What does it mean invariant? It's invariant. What do you mean exactly?
Okay, actually, no, that would be for linear maps. Sorry, my bad. Never mind.
So it is true that what I asked you to prove was that the trace of an n by n matrix, okay, is going to be the same, has the same value if you change the basis for the matrix.
Mhm.
But for that to work, so if you take, let's say, a matrix and you take the trace of this, so this will be some element of the field. Now, I'm thinking of this matrix as a linear map from f to the n to f to the n.
Mhm.
Okay, and so in other words, there's an obvious basis here that I've chosen for f to the n, which is just the standard basis. And I'm using the same basis on this side. So this is a basis, I'll call it beta. Okay, so the matrix M is really, if you want, you could think of it as the matrix of M with respect to the standard basis.
Yeah.
Okay. But of course you could change the basis. So how do we change the basis? Well, if we have a beta prime, or let's say if gamma is another basis, is a different basis for f to the n, okay? So it's not like 1 0 0 0 0 1 1 0 1 0 0. It could be something else. Like gamma could be, for example, 1 0 0 1 1 0 and 1 1 1. This is an alternative basis besides the standard one. Okay, it could be anything like that. So if I have a different basis, then what I could do is I could ask, okay, what is the basis? Sorry, what is the matrix of M relative to gamma gamma? Okay, if I use this new basis on the domain and the codomain. Okay, and so how do I figure it out? Well, I would have to put beta beta, and then the identity map beta gamma, the identity map beta gamma. So this is basically just saying, make a matrix which expresses each gamma element in terms of the basis beta and put the coefficients in the columns. And then here, this one says, find the inverse of that. Right. So this would be some matrix P M and then P inverse, where P has columns which are equal to the coefficients of the beta basis in terms of gamma. And the inverse would be the opposite. It would be the coefficients of gamma in terms of the basis beta.
Yeah.
Okay,
Okay.
but the point is that this is how we change the basis. This is how the basis, changing a basis in a coordinated way, simultaneously on the domain and the codomain. And when I say simultaneously, that's only possible because the domain and the codomain are the same. So they have the same basis. Okay. So when I do that, I change M to PMP inverse. And the idea here is that the trace of M is actually the same as the trace of PMP inverse. That's the thing that you checked.
Mm-hmm.
So this means that no matter what basis you choose to write M in, it will have the same trace. So the trace is something that is like, it transcends the choice of a basis. It's something more fundamental. It doesn't depend on the choice of basis.
Mm-hmm. Okay.
And we're going to find out why later.
Okay. All right. So, but like in terms of matrices in general, like as the trace is a map from F, or like I'm talking about n by n matrices, from F n by n to F, it wouldn't be a natural map. It would not be a natural map, or like, sorry, I lost my line of thought. It would, I think.
You probably are going to ask, is there such a thing as a trace of an m by n matrix where m and n are different?
Oh, no, actually I wasn't gonna say that, but that's an interesting line of thought, I guess.
Think about
sorry, I was gonna say like oh no, sorry, I got confused between two concepts, because like you know how you're talking about natural isomorphisms between like the dual space and the like the regular normal vector space. I was I forgot that the trace was part of the dual space. It wasn't like a mapping between the two themselves.
The trace is an element of the dual space. Okay.
Thank you.
You're welcome.
Long Tai has a question.
Professor.
Hi.
I'm not too familiar with this dual map yet, but can you provide some like the applications or like the use, like where we'll be seeing this in the future? Like how is it going to be like applied to others, subjects that we know of? Maybe like just some simple ones, like to get into it. And actually, I asked this question in the tutorial, and one of the TA told me that it's kind of like related to the integrals, and I don't really get that part, but still, maybe you have some comment on it.
I mean, it shows up in many places. I mean, the key thing to keep in mind is that, the key thing is that, so you could think of it this way, that, one of the places where, one of the places where linear algebra appears a lot is in the study of function spaces. So just imagine that you have that you have some set that you're interested in, like let's say the planet Earth, right? And you have some space of functions on it. So you have some complicated functions like temperature, which is a function on the Earth's surface, or you have pressure and such things, right? So these are these are kind of complicated types of data, right? So the data of temperature or wind speed or something, right, is very intricate. It has many, many degrees of freedom. It can vary here, it can vary there. So that means that the values of the temperature can change all over the surface, right? And so therefore the dimension of the space of possible temperatures is very, very high, because you could have different temperatures at different points and they can all be changing at different rates and so on. Okay, so the possible temperatures is a very large dimensional space. Okay, but sometimes what you want is some kind of measure, some kind of way of measuring an aggregate of this piece of data, right? So instead of telling me what the temperature is in every single location, and listing it all down in 1,000 pages, I just want one number, just to give like a general idea of what the temperature is. What would that be? What kind of aggregate data would you ask for if you just wanted a single number which tells you something about the temperature?
I guess it's related to dual maps, dual space. I don't know.
What?
I don't know. What's
Sorry,
aggregate?
I am asking you, what's your temperature? What is the temperature of your body right now? What do you think it is?
I don't know, like 36.
Okay, so what? So every single atom in your body is exactly 36 degrees? Is that what you're telling me?
Oh, so it's like the average of
The temperature of your body is a vector in a very high dimensional space, because it represents the temperature of every single particle or every single subset. The temperature of your hand, the temperature of your foot, they're different, right? So when I ask you what's the temperature, how in the world did you end up with one number exactly? You gave me the average. How did you define the average?
You just add like all them up and then divide it by.
Okay, so that means you did an integral. You integrated it. You integrated all the different temperatures and you got an overall temperature, and then you divided by the volume of your body, right? That's how you got the average, right?
Yeah.
Okay, but if I take your temperature, as complicated as it is, this complicated function, and if I multiply that function by 2, I mean, you would die instantly, but never mind. If I multiplied your temperature by 2, what would happen to the average temperature?
It's 2. Like,
yeah, so you see that it's a linear, that average is linear. It's a linear function, which has a single numerical output. That's what the dual space is about. The dual space are these measures. It's one number that depends linearly on the vector space, which kind of gives you some kind of aggregate information about all the possible different vectors in that space. So yeah.
Sorry, what's aggregate? What is that?
Aggregate means that you're taking all kinds of little pieces of information from all different places, and you're combining them into one piece of data, one piece of information, which is one number. That would be called an aggregation of data into a single number. And whenever you're doing that, if that number depends linearly on the input, right, then you're using a dual, you're using a covector or a functional or a linear function. So, that's happening all the time. Like when you do a 52-week average on the stock market, right? You're taking you're taking a vector in a 52 times 7, however many times you measure that stock price, that is going to be a gigantic vector in R to the 52 or 52 times 7 or something like that. But if you are only interested in the average, right, then what you do is you evaluate on that vector some function. That function is called the average function. You evaluate it on the vector on your huge data, and you get a single number. So that average function is an element of the dual space. And there's many average type functions. There's the 52-week average, there's the 10-day average, there's the daily average. All of those are elements of the dual space. They're different ways of aggregating the data.
So can you say that you're losing like data, like or whatever vectors, like by
Yes. So if you replaced your vector, if you have a vector in a vector space, okay, and if you were to write it in terms of a basis, that vector would be represented by a list of numbers, all the coefficients, right? So if I have, let's say I have a vector in V, right? And if I write V as a sum AI, EI, then I'm representing V as a list, A1, A2 of numbers. Okay, the choice of a basis that's the purpose of it. It allows you to represent a vector in terms of just a list of numbers. Okay, now if I take alpha, if I choose alpha in V star, a covector or a linear functional, okay, then I can apply alpha to V, and this will be a single number inside F. Right? So if I just give you the average temperature, there's no way you're going to reconstruct the temperature distribution. Does that make sense?
Yeah. So
Okay,
the whole purpose is just to simplify everything.
Well, be careful, because then if I have alpha 1 up to alpha n, and if this forms a basis,
then A has all the data like it once had before.
Then what you can do is you can evaluate each one of them on V. So if I tell you, the 52-week average, the 51-week average, the 50-week average, the 49-week average, if I tell you all those averages, then you will be able to tell me the daily averages of every day. You will be able to reconstruct all of the information. If I give you enough dual vectors, then you will be able to reconstruct. And so what we just did was to prove that the dimension of the dual space is the same as the dimension of the space. So that, if you're trying to understand the temperature distribution, maybe that's 100 dimensions. Maybe you need to know the temperature at 100 locations. Okay, but if you have 100 averages, different types of averages, right, weighted in different ways, if you have 100 of those different types of averages, then maybe knowing those averages is going to be enough to capture the entire thing. That's what we're talking about here.
Cool. That's cool. Thank you.
You're welcome.
Shizuo, you have a question?
Yes, I have a question.
Okay, go ahead.
Is the dual space of a vector space, if a dual space of a vector space itself?
Are you asking this because you're curious, or are you asking because you know that it's equal to itself?
Oh, yeah. I mean, if it is equal to itself, could we have a vector space that a dual space is equal to itself?
Okay, so there's a theorem, not difficult to prove. We could prove it now if you want, which is that if V is a finite dimensional vector space, then if I take the dual space, okay, and if I take the dual space of that, then this is isomorphic to V. Okay, now, 1 second here. So this looks a little bit suspicious. Why? Because we already proved that if V is finite dimensional, then V is isomorphic to V star. We already proved that because I proved that, I proved that in the following way, right? I said, let's say that you choose a basis for V, that determines a basis beta star for V star, and then we can define a map T, which takes EI to EI star, and that's an isomorphism. So a finite dimensional vector space is isomorphic to its dual, always. Okay, so then what am I saying with this theorem? This theorem seems like unnecessary, because if V is isomorphic to V dual, then of course I already proved that V dual, I'm assuming that V has finite dimension, and so V dual has finite dimension. And so this will be isomorphic to V dual dual. And so V is isomorphic to V dual dual, right? So what is with this theorem? Okay, so the interesting thing about this theorem is that there's a word here which is naturally. Okay, and what that means is that there is a way of defining a map from V to V dual dual, which does not depend on anything, on any choices, doesn't depend on the choice of a basis. We can define a map from V to V dual dual, which does not require, we can define an isomorphism which does not depend on any choices, any arbitrary choices of a basis, for example. Okay, so the meaning, the importance of this theorem is that it's usually not that a lot of times it's not very helpful to think of V and V dual as being isomorphic, because that isomorphism depends on some extra data that you may not have at your disposal. However, V and V dual dual, the double dual, they are naturally isomorphic. So what is this map? Okay, so now let's just follow me carefully now. So suppose that I want to define a map from V to V dual dual. Okay, so let me call this map, let's call it D, say. So if I have V in V, what is D of V? Well, D of V, I need to define what it is. What is it going to be sent to? So D of V is going to be a linear function on linear functions on V. That's kind of complicated. So this is going to be a linear function on linear functions on V. Okay, so what does it mean? It means that if you give me a linear function on V, then this thing, I can evaluate it on that and give a number. So that means, i.e., given alpha inside V dual, a linear function on V, okay, D of V, I should be able to apply this on alpha, okay, and this will be inside the field. Okay, so how do I define it? So dV is going to gobble up this linear function and spit out a number. Well, okay, there's an easy way of getting this. We can take this linear function and we can actually evaluate it on the vector that we started with in the first place. And this will be inside F. So dV is the linear function which takes alpha to its evaluation at V, where V is fixed. So another way of phrasing it is that dV is evaluation sub V, evaluation at V. Okay, for every vector, I can define the map which evaluates linear maps on that vector. Okay, so this is a little bit circular, but it's not a circle. It's just multiple steps of logic. Okay, so okay, and so I want you to try to prove, so theorem, the map V maps to dV is an isomorphism. Okay, and of course, the thing that you can notice about this is that it does not involve any choices of basis or anything. It just says that for every vector, you get a dual element. That dual element takes a dual element and evaluates it at the vector in question. If V, so maybe I should put a warning. I'm surprised that no one asked about this. So if V is infinite dimensional, so if it is not finite dimensional.
Professor, the reading of the writing is unclear.
Oh. So if V is not finite dimensional, then V is never isomorphic to V dual, and even less to V dual dual. It turns out that when if you have V, so in the finite dimensional case, and in the infinite dimensional case, things are different. In the finite dimensional case, we have V, and then we have V dual, and then we have V dual dual, which is back to V. In the infinite dimensional case, you have V, well, V, no, V, and then you have, maybe, actually, it should have a different color in infinite dimensions, V dual, and then you have and so you can keep going and they get bigger and bigger every time. So you can define their dimension. Their dimension will be infinite cardinals, and they get more and more infinite, bigger infinities. But that's for another course. Any other questions? Everyone is quiet. They're like, uh-oh, what did he just talk about? I apologize. I shouldn't have said anything. Let me just see.
Given there's no one.
He's the luckiest one up there.
Given there's
Your
no one
microphone
really
is on.
asking.
Your microphone.
Yeah, I'm asking a question.
Secondary is
But like, there's background.
Get a hold of yourself.
Yeah, yeah. I'm a bit confused on the concept of the dual space So if you could just I apologize for the background noise.
It's okay. The dual space. Okay. So this is a special case, right? And we already covered the fact that if you have two vector spaces, V and W, over the same field, that you could consider linear maps between them. And those linear maps, they form a vector space. If you have two linear maps, you can add them together and get a third linear map. Or you can scale one linear map by a number. This dual space is just a special case of that, where you take, instead of going from V to W, you go to the one-dimensional space, which is just the field itself, F to the 1. And so you see that it's linear maps from the vector space to F. So that's why I call them linear functions or linear functionals on the vector space V. They're not vectors in V, they're covectors, meaning that they are not individual vectors. Instead, they are like little things that gobble up vectors and spit out numbers. So they have the feature like so let's see. So what is V star? V star is linear maps from V to F. So suppose that V has dimension n, right? If I wanted to write, let's say alpha as an element in V star, if I wanted to write alpha as a matrix, okay, what do I need to do? I need to choose a basis for the domain. So let's say beta is a basis for V. Then I can choose basis for V, and I don't even need to choose a basis for F because it has a natural basis. It just has the number 1 as a basis. So this thing will be what? It'll be a matrix whose columns are obtained by applying alpha to each basis element. So if I apply alpha to E1, I'll get a number. So I put that number in the first column. And then if I apply alpha to E2, that'll give me another number, and so on. So this will be a 1 by n matrix, otherwise known as a row matrix. Or a row vector, sorry. Sometimes they call it a row vector. Okay, so what does this mean? This means that if I give you a row vector, let's say if I give you A1, AN, okay, then this plays the role of a dual element, right? Because if I give you any vector x1 up to xn, so this represents a vector in V, okay, x1 e1 plus xn en, and this represents a covector. This represents a dual vector, which is a1 e1 star plus an en star. Okay, And you can see that matrix multiplication, what does it provide? It gives you just a single number as the output. It'll just give you a1x1 plus anxn, which is just a number in the field. So you see that this row vector, what job does it do? It takes any vector and outputs a number, and it's a linear map. So if I multiply this x by lambda, the result will multiply by lambda. If I take the sum of x's, if I take a sum of two column vectors, this will just give me the sum of the results. So a row vector represents a dual vector. And what does it do? It is just a linear map from the vector space to the field. So this is the relation between this is the representation. This is how we represent them. We represent vectors as column vectors, and we represent dual vectors as row vectors. And a dual vector and a vector, you can let the dual vector eat the vector and you get a number. I hope that helps.
Okay, so that clears up dual space, but then dual space of the dual space. V star star.
Well, I mean, this is a
my main
space.
problem.
I mean, this is a vector space, just like V was, and so I can take the dual space of it. I mean, I'm not doing anything except iterating the same construction. So you can take, the linear maps from V to F, that's a vector space. So you can take the linear maps from the linear maps from V to F, right? You can do this, L of LVF F. This is the dual of the dual. Okay, so that seems complicated, but I'm just applying the same thing again. Okay, so, but the cool thing is that in a finite dimensional space, so if V is finite dimensional, then what I proved above is that this is naturally the same thing as V itself. So when you dualize the dual space, it ends up being naturally equivalent to V. And so in that sense, the dual operation, it terminates after one step. That, if you dualize V, you get a new vector space, which is called the dual space. But if you do it twice, you don't get a third new vector space and a fourth and a fifth. You only get V and V dual, and you don't have anything else because the dual of V dual is back to V again. So in the finite dimensional case, V by duality produces V star, and by duality, V star produces V again. Okay, that's what I meant by this. In the finite dimensional situation, it turns out that linear maps on V is actually the same thing as V. But in infinite dimensional case, you have to be a lot more careful that every time that you apply the dual, you get a hugely larger vector space. And so you have to be careful that every time you apply dual, you're going to be producing a completely different vector space. And so you can produce an infinite number of infinite dimensional vector spaces just by applying duality again and again and again. So it's kind of shouldn't be called duality because there's not just two things. The reason that this is called duality is because there's two and they're kind of related together.
So basically V star star is the map from all the maps to a specific element in the field, or it's the map.
You just have to kind of compartmentalize, right? You have to say this, what is the double dual? It's linear maps from a vector space to the field. Well, okay, which vector space? Well, that's a separate question. If you want to get into that, then let's talk about it. The vector space itself is the linear maps from V to the field. So you just have to separate it out. It's like in Dante, Dante had a certain model. He had like a mathematical model of hell, right? Which he described in this book, which had multiple layers, almost like the crust of the earth and the mantle and the core, right? Except his had, I forget, 10 levels?
7.
7. The 7 circles of hell, or what was it called?
It was the 7 circles of hell. I think it's Dante's Inferno is the.
Yeah, that's the name of the book.
Yeah.
So, this is what's going on. Every time you apply duality, you just get deeper and deeper, but every layer is just a vector space. So the next vector space is the dual of the previous one. What is the previous one? Oh, it's the dual of the previous one. What's that one? Well, it's the dual of the previous one. There's nothing wrong with just having a sequence of operations, one applied to the next. But the thing that you really need to think about, the thing that you should think about, is why I gave this careful argument, why V and V dual are the same. That's the thing which is maybe a bit surprising, and you have to think about it. Go over this explanation.
Yeah, okay, I will. I got a whole week to do it.
Yeah.
Thank you.
So Sam has a question in the chat. Sam, if you want to ask.
Sam?
You mentioned that we can think of vectors as maps from the field to the vector space.
That's true, yeah.
What would the dual space look like for that?
Okay. So what Sam is referring to here is the fact that I was explaining before that that we can any vector V inside V may be viewed as a linear map from the field to V. And this linear map is just taking lambda to lambda multiplied by V. Okay? So in particular, the unit element, the multiplicative identity, is the thing that is sent to V. So any vector determines this map, and any such map determines a vector. And so they're the same thing. So in other words, you can write that V is isomorphic with the linear maps from the field to V. Okay, but don't get confused. If you go the other way, if you take linear maps from V to F, those are linear maps on V, linear functions on V, and so this is the dual space. So if you want, you could say that because V, I guess, Sam, what you want to see is something like this, that V star is already L of F V F. But I mean, we're just making something simple look more complicated if we do this. Does that make sense? It's just for people who are obsessed with linear maps, they don't want to think about anything except linear maps. They want to convert every vector space into a vector space of linear maps. And then the dual space is linear maps. And if V, if they refuse, then you could just keep going, right? You could say L of L, F, L, F, V, F. But I mean, we're not getting anywhere. It's just giving the same thing again and again and again. I don't know if that addresses your comment, but let me know. Anytime. You can let me know anytime.
Sorry, pardon me. Could you maybe go more in depth about maybe what an element of that space would look like?
Which space?
The dual of the function from the vector space back to the field, because it can't really be like the inverse from the field.
This you're talking about? You're asking about, like, is it that you're trying to understand the dual space a little bit better, or what?
Yes, sir.
Okay, I see. Okay, so let's talk about the dual. I'll try to draw a picture. I'll try to explain it in a different way, because I already explained it in 3 different ways. but that's all right. I can use another one. So if this is V, then the vectors in V, they kind of look like there's 0, and then you have these elements V, V1, V2, V3, and so on. We have these vectors in V. So what does, there's this other vector space, which is called V dual. And I'll call it alpha 1. I'll call the elements in here alpha 1, alpha 2, and so V star is just a vector space over the field F. It's a vector space just like the way that V is. Okay, but there's a relationship between these two. So the question is, I built V star out of V. And the question is, what is V star? What are these alpha elements? Okay, so alpha 1 is an element in V star, and it's defined to be a linear function on V itself. So what does a linear function look like? Well, we saw these linear functions. So like, actually, let me give them names F1, just so that I emphasize that they are functions. So, so what is F1? So F1 looks something like this. It looks like, A1 x1 plus AN xn. It looks like a linear function, just like what we were studying in the systems of linear equations. This is F1, F2, F3. So the linear functions, they are vectors. We can add them together, right? And they look like this. They look like linear functions. And so if I wanted to draw them on V, how could I draw it? Well, you could try to draw the level sets. So you could say F1 equals 0 is going to be a subspace of V. So let me draw it like this. Say this is, let's say, F1 equals 0. And that's the level set of the function where it's equal to 0. But it also has a level set where it's equal to 1. So I'll draw that. This is F1 equals 1. This is F1 equals 2, and so on. Okay, so you could think that this vector, actually, are you seeing what I'm drawing? Is everyone seeing what I'm drawing? Oh yeah, okay. Right, so this vector is a function on this space, and so it is not a vector in this space. It is a function on the vectors. So I can draw, if I wanted to draw it, I would have to draw something like the level sets of the function. Right, so this is F1. Now, if I take F2, let's say, let me change the color of F2. Okay, F2 has a 0 set, which is something like this. This is F2 equals 0. And F2 is bigger than F1, let's say. So where it's going to have a value 1, it's going to be closer. So the 1 value will be closer. The 2 value will be closer. Sorry, this is F2. So those are the level sets of F2. And similarly, if I take F3, okay, then F3 equals 0 is going to be some subspace. And F3 is smaller here. So it's going to have its one level set is going to be a bit further out. So it'll be out here, say. This is F3 equals 1. Okay. So I'm just trying to give you some kind of a feeling for what these dual elements are. The covectors, they are linear functions on the space V. And you can't really draw them as arrows inside V. You can only draw their level sets, which are like a family of subspaces like that. And but nevertheless, you can take these functions and you can add them and multiply them by scalars and so on. So they form a vector space. So you have a choice. You could either have the mental picture where they are just vectors inside the V star vector space, or you could think of them as linear functions on V, which you can add and multiply by a constant. Does that help?
I think so. I'll think about it. Thank you.
Yeah. So when you study a system of linear equations, you're basically writing a list of dual vectors. Linear functions are just dual vectors. In that sense, it's very simple. We've been studying them a lot since the past few weeks.
Okay, so Shijuo has a question.
Okay, go ahead.
Yeah, I'm not very, I have not very understand about your proof. Yeah.
Which proof?
The there is a natural is the vector space is naturally isomorphic to the dual space of its dual space.
Right. So I didn't give the complete proof. Okay, what I did was to define the map from V to V dual dual. Okay, I did not prove that this map is an isomorphism. Okay, but you can, if you understand this map, then, and if you try to prove it, you have enough information. It's easy to prove. Okay, but the more difficult thing is not the proof that it's an isomorphism. It's the more difficult thing is to define the map itself. So I need to define a map which takes a vector in V to a dual dual vector. So I need to explain. If you have a vector in V, I should get D of V should be a dual dual vector. What is a dual dual vector? Well, it's something that eats something and spits out something. So what is an element of V dual dual? Okay, it takes so whenever you have something dual, so it takes an element of V dual and maps it to the field. This is what an element does. So an element it takes linear functions on V to F. Okay, the dual of V dual is the space of linear functions on V dual. So an element will take a linear function on V and map it to F. So if so the claim is that each vector in V defines a special element in here. Okay, i.e. it what does it do? It takes the linear function f to the number f of v. Okay, this is it. I mean, it looks like I'm not doing anything, but this is the point, is that every vector in V provides an element in V dual dual. That it just for free, it provides it. Why? Because given any linear function on V, we can evaluate it at that point, and that gives us a number. And if you change the linear function, you're going to get a different number. So you end up with an association from linear functions to numbers. So you get a dual element on the dual space.
So
Thank you.
You're welcome.
So like an element of V star star would be like a set of maps, each one mapping to an element in F. And then once we
Each one
do
mapping
all
to
that,
F. Each one mapping to F.
Each one mapping to F. And then the result of all of those maps would be a vector in V, right?
All I'm saying here is that if you have an element in V, it defines a linear function on the space of linear functions. This is the thing where you need to put your phone on silent, turn off your computer, and you need to lie down perfectly still for 1 hour, okay, and clear your mind, and then think about the double dual, and you know, eventually you will have you know, a transformation.
Hopefully.
Let me think. So
yeah, I think it's just going to take like, yeah, just some time.
I have an analogy for this, which is maybe a little bit unpleasant, but might as well give it. So imagine that you have like a whole bunch of different birds. There's different types of birds. You have pigeons, you have parakeets, you have, you know, blue jays. You have, what are the red ones called? Cardinals. Okay, there's all kinds of different birds. Okay, imagine that they are V, the vector space V. What would be the dual space? Anyone? Does anyone have an opinion? What is the dual space to the space of birds?
The set of all maps from one bird to another bird?
No,
Or
not
the
to
same?
not from the birds to themselves. It has to be to the field.
Oh,
Maps from the
Their
birds to the
food?
field.
To the
Sorry?
color?
What would be in duality with birds? The ultimate, you know, ages-old duality between
Bees.
birds and what?
bees?
Birds and bees. That's a good one.
The soil. They all die.
Birds and cats. Birds and cats.
Oh,
Okay. The space of birds is dual to the space of cats. A cat, what does it do? It just eats the bird and returns something in the field. Okay, so we have the space of birds and the space of cats. And the claim is that they're dual to each other. Okay, but suppose that we wanted to define something which was dual to the cats. In other words, we want a map which will take each cat to the field. It'll return, you know, given an input cat, the output will be in the field. For all the different cats, you have the red cat, the blue cat, the orange cat, the black cat, right? And I want to define a map which takes each one of those cats to the field. So one way to do that is to just pick a bird, a type of bird. Pick one of them, let's say a blue jay. And you feed the blue jay to the yellow cat, to the black cat, to the red cat, to the brown cat. And each one of them will produce something in the field. So what you see is that choosing a bird defines a dual map, defines a function on the cats. Every cat, you just feed it that specific bird. So in that sense, you can see that a bird determines something which is dual to the cats. And the cats are dual to the birds. So we have a double dual. So the double dual of the birds are the birds, and the double dual of the cats are the cats. Anyway, that may not help most people, but it might help some. So that's the fifth explanation of dual for you. Okay.
I'll be sure to tell everyone to check this out.
Yeah, think about it. We have to stop. Have a great weekend and great reading week. And try not to stress out. You have to try to de-stress, please. Thanks a lot, Syed.
Thank you, Professor.
You're welcome.
Thank you, Professor.
You're welcome.
Thank you.
You're welcome.